Hello everyone. As I promised you in former videos of digital signal processing, we need to look into Fourier transform because that is what we use typically to get the frequency content of a signal. And although in digital systems or discrete time systems we use the discrete time Fourier transform, which we call it DTFT or DFT. And we, in MATLAB, for instance, we use the version of it that is numerically very fast, call it fast Fourier transform. But before that, we first need to know what is Fourier transform, what Fourier transform is, in order to understand the discrete version of it. So first, let's look at the continuous version of the Fourier transform, CTFT. And then in the next video, we're going to talk about the discrete version of it and the fast Fourier transform. So what is Fourier transform? Fourier transform, developed by the French mathematician Fourier, is a technique that will give you this frequency components of the signal. Okay, and it's a very, very important method. It's a foundational method in signal processing to get the frequency content of the signal, to analyze it, to design filters for it, and so on and so forth. So let's go ahead and see what this transform is. So if you have a function in the time domain like x of t, if you multiply it by this exponential, right, by this complex exponential e to the negative j2 pi ft, and basically you know that if f is frequency in hertz, this is frequency in radians per second, and when you multiply it by the angle, this is of type angle, this is like theta. So if you do that, integrate it over time from negative to positive infinity, you are going from t domain to now the f domain here, and you get a signal in the frequency domain, which is what we call the continuous time Fourier transform. Okay. And the inverse of that is quite a bit similar. You take the frequency function, you multiply it by the very same thing, except for negative exponential is positive exponential of the same thing. And this time you integrate it over all frequencies from negative infinity to positive, and that gives you back the time function. So this is CTFT, this is inverse of CTFT. Okay. Now, if you look at this one, you can see that this one is very similar to the Laplace transform. You know Laplace transform. This is the transform we use to solve ordinary differential equation by converting them to algebraic ones. You take the signal in the t domain and you take it in the s domain. And if you remember, if you watched my videos under playlist controls, when we want to analyze the system in the frequency domain, what we did was in the Laplace transfer functions that we had, we replaced s by j omega. And that is exactly what we're going to do here. Look, if I replace this s by j omega, you are exactly going to get the Fourier transform. So if I place in s equal j omega in Laplace transform, the answer is what? The Fourier transform. Now you might say these two are not the same thing. They are. The only thing is omega equals what? 2 pi times f. So this is the Fourier transform in terms of omega, where omega is in radians per second. This top one is in f, where f is in hertz. Okay, but these are the equivalent of each other. So this is the relation between Laplace transform and Fourier transform. So we can either directly calculate Fourier transforms, or we can calculate Laplace ones and then replace s by j omega. And I'm going to do a bunch of practices for you so you learn how to do it. But next, you might ask, hey, if I give you any time function, is there an equivalent frequency function? Does this transform apply to any function in the time domain? And this integral is always you can always solve this integral and it converges to something? The answer is no. There are some conditions for it. Not every function will have a Fourier transform. So what is that? Well, one we call sufficient condition for existence of a Fourier transform is what we call absolute integrability. What is that? It means that if you integrate the function's absolute value over all range of time from negative to positive infinity, this value is finite. It's not going to be infinite, okay? So the integral of the function, but absolute value of it, right, from negative to positive infinity is not infinite. If that condition is correct and it holds, then there will be a Fourier transform. So when does this happen? That is when the energy of your signal is finite. So that means the area under the curve is decreasing as t goes to infinity, and that will have a limited or finite integral of absolute function. It's absolute integrable, like a decaying exponential, like anything that has a decay in it, right? These are all absolute integrable, or if the function is piecewise continuous and absolutely integrable. These all have basically a Fourier transform. So then you might say, what about sine or cosine of t? If there is a harmonic but no decaying, do these have a Fourier transform? Well, you know that the absolute value of them, which is always between 0 and 1, will never decay. So ideally, based on this condition, there should be no guarantee of existence of a Fourier transform for them. And that could be right, but you'll see that using the delta function, okay, using the delta function, we can still define a Fourier transform for them. If we say this function is an actual function, then we can still define something for them. So this is a sufficient condition. If you have it, there will be x of f. Now, if you don't have it, it doesn't mean that it doesn't necessarily exist. The Fourier transform doesn't exist. If this exists, it's guaranteed. If it doesn't exist, then you might or might not have an integral. And as we'll see, for these guys that are not decaying and they don't work for this condition does not hold for them. Still, using delta function, I can define something, and I'm going to show you that. But before we go there, I want to talk about something that might be a question for you. You say, well, look here. When I go from frequency domain to the time domain, look at the inverse of Fourier transform. I'm integrating over what? Over negative frequencies. Here, f could be negative. And you might say, well, how can frequency be negative? Frequency is 1 over the period, and period is always a positive time. So frequency should be positive, right? I don't know that I have ever heard a sound that the frequency of which was negative 20 hertz or negative 100 radians per second. You are right. So what does negative mean? If it's not something physical and physically does not exist, a negative frequency, why do we even have this negative? What does that mean? Well, this comes from the Euler formula. If you look at the Euler formula, which allows for complex exponentials, you know that if I calculate e to the j2 pi ft, what would you get? It is going to be cosine of 2 pi ft plus j sine of 2 pi ft. And if that f becomes a negative f and you get a negative frequency, similarly it becomes cosine 2 pi ft, this time minus sine j sine 2 pi ft. And what's the difference between these two, between this f and this f? Well, they just make this angle, this total angle, they make it positive or negative. And that is corresponding to when this angle is what? Counterclockwise or it is clockwise, right? You know that when we measure the angle in the z-plane, in the xy plane about the z-axis, we consider counterclockwise positive and clockwise negative. So basically, when we say negative frequency, we are not really talking about negative physical frequency. We are just talking about a clockwise rotation of the phasor in the complex plane, and positive means counterclockwise rotation of it. So here we account for both directions of rotation. Okay, the actual physical frequency is the absolute value of that number. It's just the direction that makes it a negative or a positive. So I just wanted to clarify on this. Okay, now that you got it, let's go ahead and look at some of the properties of this transform that we just learned. What kind of properties does it have? The first and the absolute most important one is linearity. This transform, like the Laplace transform, it is a linear operation. So if you apply Fourier transform on basically a linear combination of two signals, ax1 plus bx2 or plus minus, the result of that is going to be a Fourier version of x1 plus b Fourier transform of x2 and plus and minus. So the operation is absolutely linear, and that is one of the best things about it. Then we have time shifting. If you shift the time in a signal, you have a delay or something, and you take the Laplace of a time shifted version of a signal, you get the Fourier transform of the original one, but multiplied by a negative exponential, where here the time in it is going to be that delay time, okay? And this negative is showing itself here. On the other hand, if you have a frequency or Fourier transform of a function, but you shift it in the frequency domain, so you move it left and right in the frequency domain, in the time domain, again, that is the inverse of the original function, but multiplied by what? By an exponential, but this time the exponential is positive, not negative. So although that's negative f naught here, you get positive f naught in the exponential. The other thing is convolution. If in the time domain two functions are convolved in the frequency or Laplace domain, the answer is going to be the product of their frequency content. And if you forgot what convolution is, I'm going to make an individual video on convolution in this playlist and talk about it a lot, but just remember that if I have x1 star or asterisk x2, right, convolution of these is an integral from 0 to t of basically x1 of tau and then times x2 of t minus tau integrated over d tau. Okay, and this convolution has commutative properties, so it's also equal to x2 asterisk x1. The order doesn't matter. Okay, and we use this convolution a lot in signal processing. I have a video for that under my playlist Computer Vision, and I show you how to use convolution in images to filter the images, get edges, and so many other things. But I'm gonna have a separate video and show you how to perform it even in a 1D signal and what does it actually do. The last property that I want to mention, and these are not the only properties of Fourier transform, these are the key ones. There are a ton more of properties, and they are all basically related to the properties in a Laplace transform. So the last one is called the Parseval theorem. Parseval's theorem says if you square the signal and integrate it, which is basically what we call energy of the signal, whether you do it in the time domain or whether you do it in the frequency domain, the energy of the signal is equal. And of course, the energy of a signal does not depend on how we represent the signal. Do we show it in the time domain, S domain, frequency domain, some other domain? The energy content of the signal is not going to be any different. And in a separate video, I'm going to talk about the energy of the signal and the power spectrum later, once we know enough about the Fourier transform and signal to noise ratio and a bunch of other things. So that video will be one of my future videos coming. Okay, now that we know them, let's go ahead and look at some common Fourier transform pairs. So if in the time domain you have the delta function in the Fourier transform, that is 1. If you have a constant like 1, it is, on the other hand, it's going to be delta function. And that is the interesting part. If you remember, let me tell you, if you remember a 1 in the Laplace domain, it was 1 over s. And if I replace s with j omega, you will get 1 over j omega. Okay, and what kind of function is this, right? Well, clearly you can see that at omega of 0, the magnitude of it is infinite, and as it goes to, as the frequency gets bigger, this function drops and it has a complex part to it. But you can show that if you do integral, you can show that 1 becomes what? The delta function. And of course, an exponential function will just a pure exponential. with complex component becomes delta function shifted, okay? And then a cosine function is going to be a combination of two deltas, one at negative f naught, one at positive f naught, both of them with magnitude half. And then an exponential function multiplied by a signal where the signal here is the step function. So this u is a step function, okay, unit step function. So this is just an exponential which only exists for positive time values. The Laplace of that is going to be basically this. And you know that in the Laplace domain, e to the negative at times unit step of t, if you remember, it was 1 over s plus a. So all you need here is to replace that a by j omega, or for omega, if you replace by f, it's going to be j 2 pi f. And so you're exactly going to get this, right? So you see that this one clearly, or this one clearly, easily come from the Laplace transform. If you have a rectangle, which is a pulse here, we're going to see a pulse becomes a sinc function, and a sinc function becomes a pulse in the frequency domain. So what is sinc? I'm going to show you what this sinc function is, okay? But here we're going to work through a few examples and learn how to get some of these. So we have a bunch of examples. This one, I guess I already showed you. We don't even need to worry about that if we just use the Laplace transform. But if you want to use the formula of the integral itself, well, x of f was what? It was integral from negative infinity to positive infinity of x of t, which is this function, times a negative exponential with complex, and it was this, and then integrate over time, right? So here you have to merge these two exponentials, so you get e to the negative t times what? A plus j 2 pi f. And you know that integral of e to the negative t times anything, as you know, is what? It is going to be basically that function divided by the coefficient of t. So it's going to be e to the negative t times a plus j 2 pi f divided by negative a plus j 2 pi f. So that's the function, and it has to be evaluated at negative and positive infinity and subtract. Okay, so what would you get here? Well, at negative infinity, this becomes positive infinity. At positive infinity becomes 0. So clearly this does not converge, right? That's why here, if we go back in the table, we said that it actually should not be just negative exponential. It should be negative exponential times unit step function. What happens if you bring in the unit step function? So here we have to add a u of t to it. When we add the u of t, remember this unit step function is only 1 when t is bigger than 0, huh? And before that, it's 0. So for negative t's, it's 0. For positive t's, it's 1. If that's the case, then your integral is not going to be defined over the whole range of negative, positive, infinity. It is going to be defined over from 0 to positive infinity. Okay? And the rest of it is going to be the same. The rest of it is perfectly going to be the same. Well, let me put this, so that is this part here. And so the only difference is now this is going to be from 0 to that. And so at positive infinity, this is going to be 0. At 0, this is going to be a 1. But there is a negative for that. And that negative with this negative would cancel. So you get 1 over what? A plus j 2 pi f, which is exactly that one. Okay, so pay attention that this should be only from 0 to positive infinity, not negative. And of course not. Why? Because when t goes to negative numbers like negative infinity, this signal becomes extremely large. and the signal is not going to be decaying, it's actually going to be increasing exponentially. So we can only do it in a range of 0 to positive infinity, and that is achieved by multiplying it by a step function. Okay, so this is what this is for that part. Now, if you go back, maybe you say, what about the delta function? So let's go ahead and look at the delta function. So for the delta function, so the x of f is what? It is the integral from negative infinity to positive infinity of delta function times e to the negative j 2 pi f t dt. Now you know that the property of delta function is what? This delta function at 0, it has an infinite magnitude basically, and anywhere else it's 0. And the integral of delta function from negative infinity to positive infinity is 1, right? So that's the Dirac delta function. Okay, we call it the impulse function. So, and this delta function, remember that it's always 0 if t is not equal to 0, and when t is 0, this function converges to infinity. So this whole integral only has value when t is equal to 0. At non-zeros, this has nothing. So you only need to basically focus on this function when it is 0. And what happens when this function is 0? Yes, it's 1. So this function at 0 is 1, and then the integral of this is also 1, so you get a 1. So you see your delta function, the Fourier transform of that is what? It is 1 here, right? Okay, now that we have checked this one and this one, you might say, how about this? Pay attention that this function has a constant magnitude of 1, so it's not absolutely integrable, and the energy of it does not go down. It has an infinite energy, and so in the sense of performing this integral, right, if I just plug it back into the formula here, if I go right here and plug in x of 1, what would you get? Look, you have this complex function, and this one, time goes to negative infinity and positive infinity. Now, of course, the magnitude of it does not go up because it's a complex exponential, so magnitude of this is equal to 1. But when you integrate it over this big range, the energy is infinite. So if you just want to perform this integral in the traditional sense, there is no Fourier transform. So you might say, well, where did you get this delta of f from, right? You said this is the Fourier of that is delta of f. Where does that come from? Well, here I'm going to show you the result, but backwards. So I'm going to do the inverse transform, and in this inverse transform, instead of x of f, I'm going to plug in what? Delta of f here, right? So if I plug in delta of f here, what is the result? So let's go ahead and get it. So x of t equals integral from negative to positive infinity of delta of f times positive complex exponential integrated over frequencies. And remember the property that I told you, that the integral of delta of, let's say, f, for instance, and any other function of f, let's say g of f, df, if you integrate it over the whole range positive to negative to positive infinity, this is just going to be g at 0. So that's the same thing here. This is the g of f. So if you plug f of 0 in it, what would you get? You get e to the 0, which is 1, and that is exactly what you will get. So you see, if I apply the Fourier inverse to the delta of f, the result is 1, and so I can claim this. Now pay attention that delta function is not any traditional function. This function does not physically exist. This is a function magnitude of which goes to infinity at 0, and everywhere else it's 0. So that is not really the kind of normal function that you might want to deal with, but we can use that spike at 0, right, to say that this is for x of t equal 1, or for that matter, any constant value. The frequency version of that is that same constant, whatever it is, times delta of f. And frequency-wise also it does make sense. How? So if this is the magnitude of x of f, and this is f, this function here is just a simple spike at 0 like that. Well, is that true? Yes, because when you have a constant value, does it change? Is there anything that varies in it? No. So the only frequency that a constant has is a frequency at 0, a DC frequency, and that is exactly here. There is no variation in the signal, so the only frequency in it is at 0, f of 0. And so that physically does make sense. Now, similarly, if I have an exponential, complex exponential, in the time domain, the answer of that is going to be the delta function, but shifted. And that you know from these key properties. If we go and look at these key properties, that is which one? That is this guy here, the frequency shift. So of course that directly comes from that property, right? So a complex exponential, instead of this being at 0, it is now shifted to the right at f naught, basically. It's going to be a spike at f naught. The next one we're going to see are cosine and sine function. Remember I said these functions, their energy is not finite. So again, similar to this one, they don't have a Fourier transform in the normal manner. But I can show you, if we use these two properties, this one and this one, I can get what? I can get the cosine function. How? Let me show you. So you know that the cosine function can be written as 1/2 e to the 2 times that input argument times j plus 1/2 e to the negative of that, right? So this is what we use from the Euler's formula. There we go. So the frequency of that is going to be 1/2 the Fourier of this plus 1/2 Fourier of this one. And based on what we just learned, this property that we just learned, right? If we have a positive exponential in the frequency domain, there is negative f. If this is negative exponential, that's going to be positive f. And that is these two that you will see. So if you look at a cosine function, what would you get? You get one spike here at positive f naught, and you get a symmetric version of that on the other side at negative f naught. And of course, the frequency of a cosine function, 2 pi ft, is f naught. But you see there are two versions of that, positive and negative. This means the rotation is counterclockwise. This means the rotation is what? Clockwise. And that's the same thing. And you might say, what about the sine? Is the sine going to be similar? Sure. So if your function x of t is sine of 2 pi f naught times t, based on the same thing, this is going to be 1 over 2j, correct? And then e to the j 2 pi ft, and then minus e to the negative j 2 pi ft. So if you calculate it, what would you get? The x of f for the sine function is going to be 1 over 2j delta of f minus f naught minus delta of f plus. And this is, by the way, f naught. So like this. Okay, so now that you have the function, how does it look like? If I want to plot them both, because look here, you have a complex component, you have j here, right? In the cosine, you did not have any j, they are just 1/2. But here is different. So if I want to plot them for cosine of 2 pi f naught times t, and then for sine of 2 pi f naught times t, remember, in general, they could be complex numbers. So this is the magnitude, this is the phase, right? If I call the Fourier transform of that x, this is magnitude of that x of f, this is phase of x, and both of them versus f. So for cosine, you clearly have one spike here, one spike there. The height of them are 1/2, and they are at negative f naught and positive f naught. And at both of these numbers and everywhere else, because remember they are both, there is no j in it or anything, they are magnitude 1/2, so there is no phase, they are real. Therefore, the phase here is 0 and the phase here is 0. Okay, so this is for cosine. But if you do it for sine, the magnitude is going to be similar. They are still 1/2 at those frequencies. So you get again the same thing, 2 spikes, because that's the same thing, that's the same frequency, right? But if you look at the phase, this time the phase is not 0. What are the phases? So at positive f naught, the phase is negative pi over 2, and at this point it is positive pi over 2. And where do they come from? Well, they come from this definition, 1 over 2j. So what I can do to this, I can multiply both numerator and denominator of that by a j, right? And now you know j squared is -1, so you can also write it as negative j over 2, right? And if you multiply it, it's going to be delta of f minus f naught and positive j over 2 times delta of f plus f naught. So you see that at the frequency of positive f naught, which is this one, your magnitude is 1/2, but with what? With a negative j, and negative j corresponds to a phase of negative pi over 2, and at the frequency of negative f naught, you have positive j, which corresponds to a positive pi over what? Over 2, and that is what you can see here. So these are what? These are the sine and cosine. Okay, so I guess I showed you that one as well. So now we have all of these taken care of. The last pair that we want to look at is a pulse that becomes a sinc function, and the other way around, the sinc function becomes a pulse. So let's look at this last one here. So what is a sinc function? What is a pulse here? So a pulse here in the time domain is defined as a function that is 1 between negative t over 2 to positive t over 2 and elsewhere 0, right? So that's a pulse like this. Now, if I calculate the Fourier version of that, right? So I multiply x of t by this function. Remember, for x of f, this guy goes from negative to positive infinity, but this function, this x of t, only exists between negative t over 2 to positive t over 2, and the magnitude of it is 1. So this is step number 1. In step number 2, you replace x of t by 1, and since it's only between these two limits, then your limits from positive and negative infinity would change to positive t over 2 and negative t over 2. So this is the integral that you need to calculate. And how does this become this T sinc of Ft? Let's calculate that. So this is the integral of negative T over 2 to positive T over 2 of e to the negative j 2 pi Ft dt. And as you know, the integral of an exponential is the exponential itself divided by the coefficient of the variable, which is t here. So you get this. And this function should be calculated at negative and positive t over 2 and subtracted. So it is going to be 1 over, or negative 1 over 2 pi j f. And then in that one for t, you replace it. So it is going to be e to the negative j 2 pi f. Now that 2 and that t over 2, they can cancel, and you can just get pi ft. And minus e to the, now that negative and that negative would cancel, so you get positive j pi ft. And this, from the Euler formula, as you know, it's going to be negative 2j times sine of pi ft. Okay, there we go. So now that negative and that negative cancel, that 2j and this 2j would cancel. And if you simplify, you are going to get sine of pi ft divided by f. And if you want, you can multiply it by a t and divide it by a t. You make it like this. And now if you define a function, right? By the way, there is a pi left that I forgot to add, so there is a pi here. Now, if you look here, if I define my function sinc of x to be sine of pi x over pi x, then these two are very similar as long as you define your x to be what? To be ft. So this one can be written as t times sinc function of what? Of x, which is what? ft. So it's going to be t sinc of ft, and that is exactly what we have over here. Now, what kind of shape does this function sinc have? The sinc looks like this. It has a big peak in the middle, and as it moves away from the center of frequency of 0, these peaks start dropping. So you have this peak, you see the peak goes from this to this to this. So if you continue this, it's going to get smaller and smaller, and it converges to 0 magnitude as it's going to infinity, right? So it is going to go like this. So this is your sinc function. And you can see from here too, right? When x goes to 0, this is like sine of 0 over 0, which converges to 1. So this magnitude is 1. And when x goes to any infinity, positive or negative, this is going to converge to 0. And that is exactly what you can see here. So that means that you have a lot of 0 frequency or a lot of constants in this signal. But as you move into higher frequencies, you still have higher frequencies, but the further they are, the further these higher frequencies are, their magnitudes are smaller and smaller, right? So you have some low frequencies. As you get to higher and higher, the amount of them in the signal in this guy becomes smaller and smaller. And if you want to give you a good understanding of it, I invite you to look at the Fourier series for a pulse function. Let me show you that here. So if you look at the Fourier series of a pulse or a rectangular function, and I have it on my channel too, you can see that that the magnitudes of these frequencies get smaller and smaller. So I recommend you watch this video I have under my mathematics, engineering mathematics, called Fourier series. And I have applied it to a pulse, and you can see that as the frequencies are increasing, the magnitudes in these frequencies are decreasing. So you go from 4 over pi to 4 over 3 pi to 5 pi and so on. So the bigger frequency it is, the smaller the magnitude of it is. And then if you look at when I run this MATLAB code, which I guess you should be able to download, you see that, look, on basically all the way to, you see that as the number of terms in the Fourier series changes, you can see that for this pulse, you get your total Fourier series to get closer and closer to it. Now, of course, here you have these ringing effects, but clearly you see that these small changes that the higher frequency term are bringing is to get your signal closer and closer to the actual pulse. So you see, the first 2 or 3 form the basic shape of the signal, and the higher frequencies only get them closer and closer, but their contributions are much smaller. So when you look at this plot, this absolutely makes sense. That to make this, you need a big fixed number, probably in this case 1/2, and then you need a bunch of sines and cosines. First, some magnitude for the low frequencies, but a much smaller magnitude from the high frequencies to regenerate this. So this is your sinc function, and that is for rectangular. And clearly, you can show that the opposite of that, if you apply a sinc in the time domain, then in the frequency domain, you're going to get a rectangular, okay? So if you have a sinc function in the time domain, you only have a limited range of frequency in the F domain here. And you can clearly see that. By the way, it has only a real part and there is no imaginary part to it. So it's pure real, as I showed you. Okay, so hopefully now you know some basics about continuous time Fourier transform, why we use it, under what condition it exists, what is the negative frequency, what are some key properties, common pairs of it, along with several examples. And we're going to use more and more of it in the next lecture when we talk about the discrete time Fourier transform, DFT, DTFT, and finally FFT. Thank you so much for your attention, and I'll see you in the next video.